Okay, let me, what's this? Okay, can you see my screen, the slides, or you are seeing something else?
We see the presenter view.
Oh, okay. Yeah, that's not good. Let me change. How about now?
I think that's what you were going for.
Okay, that's good. Hi, everybody. And, I'm glad you guys joined again for another session where we learn the latest zero knowledge together. So today I'm going to cover a little bit of I think a more advanced topic, but we also have a lot of practical applications called recursive zero knowledge proofs. So previously we have talked about using zero knowledge, proof to show, some statement is true, without disclosing everything. So in today's talk, we're going to cover, the recursive version. So what does that mean? So previously, if Alice sends the Bob a proof and Bob verifies it, we know the proof that some statement attached to the proof is good, right? So we are not saying anything about, what the statement is, right? Because in reality, the matter of fact is the statement can be anything, right? We talk about a few examples. It can be like a roll up saying, a batch of transactions that are all valid, or in Zcash saying, oh, this just single transfer shielded transaction is legit. Or we have some example, let's say battleship, right? So this hit or it's a miss, right? This statement can be, in theory, can be any so-called NP statement, non-deterministic polynomial statement. So pretty much all the computation you can think of that the computers are doing today. So when we think about recursive zero knowledge, just add one thing into the whole picture. The statement itself can also contain, whether another proof is valid. It's almost like that's why it's a recursion, right? Within this proof, if I prove this proof is good, verify this proof is good, that also infers some inner proof is also legit. Does this make sense so far?
Yes.
So
is it a fair assumption that the inner proof does not need to be the same as the outer proof? So recursion can occur, but also you can have linked proofs that are not recursive necessarily?
Yes. So yeah, that's a good point. So basically that's hi Brandon. So basically as I talked, right? So just zero knowledge is used to prove some statement is true. So the statement can be anything, as I said, right? So it can be, the inner proof, as you just mentioned, can be similar structurally with the outer proof, but it doesn't have to. It can be anything. For example, I'm proving, this. Let's, for example, I'm just using, or even, give an extreme example. I can use, let's say, snarks is 109, right? We talk about ZK snark. So the outer proof can be ZK snark, and the inner proof doesn't even have to be using the same algorithm. It can be like, I don't know, you guys, you can even be like bulletproof 09.
Cool.
So it can be, because the 09 can prove arbitrary statement, right? So it doesn't bound the inner proof that whether it's the same with, so I think that's why in this, I call it recursive. So, but you can think of it's just in the name only. It doesn't have to be like a, recursive program. The outer function and the inner function has to be, it's just a sub problem. It doesn't have to be. Okay, that's good. So just give a real world analogy, where this recursive zero knowledge come from. Let's say, for example, you went to, let's say you go to some, like, let's say a national park, right? Let's say Yosemite or, the Yellowstone, whatever. So you go there for a week, right? So, and then you want to prove to a friend by sending him pictures saying, hey, I'm in this point of interest A, first day, I go to the next day, I go to point of interest B, and so on and so forth. So at the end of the week, you're going to send him some pictures to show you, hey, I just spent 1 week in, let's say, Yellowstone, right? But you can do it in 2 ways, right? One is, on Monday, you go to spot A, you take a picture, and then on Tuesday, you go to another spot B, you take another picture. So you keep taking 1 picture every single day. And then at the end of the week, you can send 7 pictures to your friend and then say, hey, that's a proof I'm in Yellowstone for the entire week, okay? But then your friend, for whatever reason, he wants to challenge you. Hey, I'm in the rural area, my connection is not good. Now, don't send me like 7 pictures. Just send me 1 picture. Can you do that? And then you can somehow still convince me, I've been in the park for 7 days. Okay, how would he do that? How would you do that? So the idea here, I think you can almost get a clue from here, from the slides here. So the idea is, on Monday, you're still doing the same thing. You go to spot A, you take a picture, potentially with a calendar, right? So with a clock, a wall clock, whatever, calendar on the wall. So you take a picture and then you go on Tuesday, you go to spot B, you take another picture, but with only 1 trick. You also put the picture you took on Monday, you hold it in your hand, and then you take a picture on Tuesday. So on Wednesday, you're doing repeat the same process. So you're holding the picture you took on Tuesday, and then you take a picture on Wednesday. So you keep going until you reach Sunday. So let's say the picture on the left here, right? So then you just send at the end of the week, right? You only have 1 picture, which you can see if you just send this 1 picture. I mean, of course, we assume here the picture is legit proof that nobody's playing tricks on pictures. So if you just send this 1 final picture and the friends see it, you can be sure you have been in the park, for the whole week, right? Does this make sense?
Yeah, it does.
Okay. Yeah. Now some other people even saying, yes, this is even better example if you use it for parking. Let's say you park in front of a place for 1 week, and then every day you want to make sure you pay the parking ticket. So but somehow you can only put 1 envelope in front of a car. So you can every day you take the picture with the old picture in your hand. So that's a high level, that's the idea. Is pretty much you have a proof, when you're verified, and the proof itself contains, validity of other proofs. So it's a proof of a proof of a proof of a proof. You can keep this going for almost like inception level. Depends on your use case. So same thing for, going a little bit back to the zero knowledge terminology. So let's say we have a snark, which is the major zero knowledge protocol we are focusing on right now. So if you have a snark, basically you're proving some statement, right, in the form of a circuit. So the circuit itself, because the verifier, right? So you have a prover, you have verifier. The verifier itself is also doing some computation. What's this computation? It involves you are running the snark verifier algorithm. Anyway, it's still a computer program, right? So how do you do recursive snark? You basically, you're proving, because you are using snark to prove a statement. And this statement usually represented in the circuit format. But then the only trick here you do is you also put the verifier in the form of circuit, in the big circuit. Because you snark, you can prove any computational statement, NP. Right? So the statement itself can be another verifier. Does this make sense so far? So that's how you on the high level, how you achieve recursion.
So before the close of one circuit, you enter into another circuit, the result of which will either be a pass or a fail.
Yes,
passing to the tertiary circuit or failing for the original snark, wrapping up the process. Is that correct?
yes. So when you use snark, right? So if we can go back, let's briefly jump back a little bit. So, if you remember when we started at the very beginning, we are saying, hey, you can use snark to prove, any function statement, right? So this function here saying it can be anything. So what if, here we have a verifier program, right? So this is, we've run a verifier algorithm here. If which is also a statement, is another computer program, right? So this can be an arbitrary program. So we just, in F, this F can be just the verifier program. That's the only trick here. Because usually you may prove some like, let's say, Sudoku is good, or some Wordle, some Battleship, which is some statement. But the only here is, this is also a program here, right? Verifier program. You have inputs, you have outputs. So you put the verifier program inside this function. It can be the function itself, but most time is, you are verifying not only the verification is good, but also something else. So that's the only trick you do, because this is generic. It can be anything. So you can be the verifier itself. Make sense?
Yes.
Okay, very good. Okay, let's keep going. I think it's a little bit abstract, so let's put some concrete examples to see, what is useful, and then, why do people, how are we going to use it in reality? Okay, this is another example. I think this is even came out recently. I think it's just a few weeks ago. On Ethereum, they use this recursive ZK snark to prove the so-called each degree of separation numbers. So for people who have not heard about this, you probably heard about Kevin Bacon numbers, or in Hollywood, or you may heard about Erdos numbers in math. So how many of, I don't know if you ever heard about this term before, degree of separation numbers? Okay.
Yeah.
So
it was a game when I was a kid, at least. I'm 37 now. So you used to play, it was like a memory game to see if you could remember a way to get from one celebrity back to Kevin Bacon.
Yes.
Right.
Yeah.
And if they had been in a movie or a TV show or a commercial
Yes.
together, you could link them together in that way.
Yes. So it's a degree of separation. Basically, you're counting, how many hops between you and the center of the network, which is, for Ethereum guys, they treat it as a Vitalik. So how does this work? It's all similar to Kevin Bacon numbers. So let's say if you and Vitalik is a friend, so that's count as separation of one, right? Distance. Pretty much you are treating like a Vitalik at the center is a source, and then you are counting how many hops you have to jump before you can reach Vitalik. And then if you're a friend with Vitalik, he's going to sign with his, like, I think pretty much his public key. So you can verify there's really a connection over there. They do this offline, of course. So basically, let's say if Alice is a friend with Vitalik, then his ETH DOS number is 1, right? And Vitalik's ETH DOS number is 0. And everybody else is positive. So if Alice is friend with Vitalik, then his DOS number is 1. And if Bob is friend with Alice, but he's not direct friend with Vitalik, then his DOS number is 2, right? And then so on and so forth. You can actually generate proof. That's what this app does. So you call it ETH DOS. So the high level idea is, let's say if Alice, he can have a proof, right? He can have a proof that says my DOS number is, let's say, N. And then Bob is a friend of Alice. And then Bob can generate proof, right? That his ETH DOS number is N+1. Okay, how is that done? You can almost feel, right? It's recursive, right? Because I'm going to generate, and Bob, he's going to generate a proof for the following statement. 1, Okay, somebody else is, okay, Jay is joining, okay. So at Bob, okay, remember, okay, once again, so Alice has DOS number of n, and Bob is a friend of Alice. And Bob now wants to prove, his DOS number is n plus 1. So he's going to generate zero knowledge proof. How is he going to do that? He's going to generate a proof for the following statement. 1, I am a friend with Alice. They can prove some kind of like a signature within the circuit, right? That's doable. And 2, Alice has a proof that his Ether's number is n, right? So you generate this for this, the 2 statements together. One is Alice is a friend of mine, and also Alice has a proof his Ether's number is n. So if I can prove these 2 together, then that means my Ether's number is n plus 1. Does this make sense? Any question regarding this?
That makes sense.
Okay, so now you can clearly see, right? This is a recursive, right? Because Bob, when he's generating the proof, this proof can, derive from another proof that Alice's proof is legitimate, is valid. So if I get a proof from Bob saying, hey, if I can verify Bob's proof, then I'm sure Alice's proof is good, right? Because that's part of the proof. The bigger proof I'm verifying. So if everybody does that, you can then pretty much, if you can get any, it's almost like web of trust. If you can have anybody who already has this number and you are a friend with that person, then you can generate your own numbers, Ether's numbers. And here's the trick. Here's the cool thing. You don't have to trust anybody, right? Because if I just give you, hey, my separation from Vitalik is 5. You just give me the proof. I verified. I know you are definitely 5 hops away from Vitalik. I don't have to trust anybody. You can always just give me the proof. And this proof can be, it's generally distributed, right? I don't have to ask anybody else. So this is the basic idea for Ether's numbers, which I think, yeah, it's pretty cool. I think I'm even asking all the people in the Bitcoin space, I think we can change this version to a slightly better one, because instead of counting the extra degree from Vitalik, we can say, hey, how many degrees from Satoshi himself, right? So we can call it, Bitcoin DOS number or Satoshi DOS number. It's the same, it's the same algorithm, but which is a fun idea for people who have been listening or watching here live, or later on you can choose to work on. How cool would be that? And you can actually have Satoshi signs for you. So that's another additional, benefit. So call it Satoshi DOS, whatever. Yeah. You can take this. It will be a fun exercise. And you can pretty much reuse the code base they have. But of course, you can switch out. Instead of running on Ethereum, you can switch out and running on Bitcoin. So Bitcoin DOS number from Satoshi. So just an idea out there. Okay, so we see a concrete example, but now let's get a little bit of into a more high level. So why do people even want to do the recursive zero knowledge, and what are the more practical benefits you can get from them? I think I listed 3 things here. One is, I think I showed a little bit earlier in the Ether's number example. So it's not, you cannot see it there, because in the outer proof you are only verifying the validity of one inner proof, right? Think about that, because the statement can be anything, so it doesn't have to be the inner proof. Can have a multiple inner proofs, right? So for example, as the example I show you on the right, let's say you have many proofs, right? So let's think about this one roll up. In the roll up applications, basically you are batching many application transactions. You can each generate a proof for, let's say, each transaction, and then it's got one proof, right? And then once you can even organize them into a tree. So if you have two proofs, you can generate a recursive proof saying, hey, this proof is valid if and only if the two subproofs are valid, right? And there's no stopping you from even going higher. So basically, you can organize in the tree, you can merge them. Instead of have, let's say 8 proofs, you submit 8 transactions joined to the chain. You can aggregate all of them into one single proof. And this one single proof is pretty much like a compression of all the proofs aggregated. So if this proof is good at the top, all the proofs, all the transactions in the leaves, they're good. So this is very, you can see this is very, important in the blockchain space, right? Because you are, even for Bitcoin, right? We have a very cheap fees, but still you want to minimize the kind of things you push onto the blockchain. Make sense so far? Okay. Okay, that's good. So this one big application, I think we even internally we think of some schemes to make this happen. So for example, in the battleship, right? In the worst case, right? If you just guess and you're out of luck or whatever, you can play almost up to 100 steps. So you are pretty much, you are missing off the steps you can miss. So you are playing, every move is one transaction, right? So still you can have almost like 100 transactions. So instead of having this 100 transactions, think about using recursive snacks. You can merge them into a single one. So this single one is valid. It can be verified if and only if all the 100 subproof they are valid. So that's one benefit, right? Which is you can think this is huge. So another one is parallelism. So what does that mean? So a lot of time, as I mentioned before, for practical snacks, the bottleneck, the number one bottleneck right now for this to be deployed everywhere, on every device is kind of computationally intensive to generate proof. So as a prover, basically he has to do extra work. And this is generally, if the larger the computation is, the more time it takes. And not only the CPU time, but also the memory. So at one point you are going to say, hey, it's going to be like a showstopper. You cannot generate the proof efficient within a reasonable amount of time. So what you can do here is, instead of, doing the big computation, let's say, for example, you want to prove, let's say, again, I use the roll-up transaction example. So let's say you want to do roll-up for 8 transactions here. And so the usually is you put this validation for 8 in the big circuit. The circuit almost like a loop. The loop at the top, it says, loop this 8 times. And each time validate transaction I, right? So this is usually how you do that, almost the monolithic zero knowledge. That's how you do it in a roll-up. But this is going to be slow, right? And also the memory is going to be big because it's almost, proportional to almost like a linear, quasi-linear. It's a little bit worse than linear, but you can think of it as linear. So the bigger, the more transactions you're going to have, the slower you're going to have to generate the proof. So what you can do is, instead of doing just one gigantic circuit you want to prove, you are breaking up. Maybe I can do for each transaction here, I can generate a proof. This transaction is valid. And then what's the benefit of that, you may ask. So here's the benefit because all these are independent, right? You can generate the proof for each of them independently. That means they can be done in parallel. Because previous example is if you have a big circuit which has you validate 8 transactions, it has to be done sequentially. You do the first transaction, you do the second. You cannot be that you cannot do it in parallel. So in this example is, you have a transaction 1, 2, 3 up to 8. So you are generate the proof for each of them at the same time. And then you are merging them. So there's some overhead of a merging, but usually if you have more transactions, let's say, for example, you can think about this as 1,000 transactions. So you are saving almost, it's much faster than you do the, the gigantic circuit for 1,000 transactions generate proof monolithically versus you break them down into each transaction, and then you just keep merging the proof until you only have one proof. So this is much faster. And also memory wise, it's also save you a lot of memory, right? So that's one CPU wise, you can save a lot of prover time if you can use parallelism, right? The second part is even for memory. For example, now you have a computation which is gigantic. For example, you want to do some like a machine learning training. You need probably some almost like data center to process for a long time, many machines with huge memories. But then if you want to generate proof for this kind of computation, it's almost impossible today, right? Because you pretty much blow up the whole thing. And then what you can do is, instead of doing this gigantic computation, you just cut them into chunks, small chunks. And then each chunk, you generate proof. So this is what the third one I've come to here. So basically, you can incrementally verify some gigantic computation, which you cannot generate proof otherwise, because it's going to be too big. So for example, I just mentioned one example. You are training some machine learning model. Because the computation, even when you are just re-execute it, it's going to be gigantic. So you're going to blow up your memory or even CPU if you just generate the proof for the whole thing at one go. So instead, you are breaking them into, let's say, many pieces. And then for the first piece, you generate proof. And then when you generate the second proof, this proof not only saying, hey, the current computation is good, but also the previous proof is good. So you're doing this like iteratively. So every step, you only have one single proof, which pretty much collapse all the previous proofs. So think about even in the blockchain space, it's also, there's even another more explicit example. So think about each block, right? So let's say this is a big Bitcoin block. This is Genesis block. This is the block 1 till now. I don't know how many, probably like close to 1 million, right? So every time you can generate one proof. So let's say proof 1. What does this say? It says, oh, the Genesis block is legit. It means all the transaction within is good. And then when you generate another proof for after you have block 1, block 2. So this not only says block 2 is good, but also says the previous proof is legit. Right? So you're using recursive 0.9 to collapse, to compress all the previous proof into a single proof. So at any given block height, you only have one proof, which says if this proof is verified, I know all the previous blocks as good. So you don't have to, you can always incrementally verify the computation you want to have. So I think that's probably a lot of information. I pause here for any comments.
I'm just trying to conceptualize,
I hear you clearly, Brandon. Am I only one or anybody?
No, that came through like a robot for me as well.
Okay. Brandon, you want to try that again? Okay, I don't think I can hear you. Okay. You can either type in the chat box or somebody else can, jump in and
Yeah, I couldn't understand. So here's what I was going to ask. If we're looking at this and we're saying one proof to verify them all, right? In the analogy you just gave, the one proof to verify them all is going to be the last block.
Yes.
That's it. Okay. So if we know that to be true, then what we're saying is you can't verify the entirety of the blockchain in one pass. What you're really going to try to do is go as far back as you can. In this case, we have a known block called Genesis, and start from there and validate everything from Genesis to this current block if you have to say the next block is valid. Yes, no?
Can you repeat that thing? Is saying yes.
Right,
So let's say, for example,
so,
the nth block. Okay. What are you asking here?
so what I'm asking is if we take a look at the diagram on the top, right, and
Okay.
the bottom row, they have a collection of proofs that say single proof. If we
Yes.
were to replace the bottom left one with block one,
Okay.
bottom left, right, and then to move to the right, it would be block two. And
Okay.
move to the right, that would be block three.
Uh-huh.
Right, the one proof to verify them all actually does have to go through and map and verify each of these blocks on its own before the green block at the top can show a positive result. Is that
Okay.
a fair assumption? Yes?
Actually, no. Okay.
No, okay,
So this is a little bit different. Let me differentiate. I think, yeah, it's a good question. So, okay, you pretty much, let's say you have, for example, you have 1 millionth block. Okay, just assume this, you have 1 millionth block. Now you want to generate proof. You know, all the blocks up to this block is legit, right? You have two ways to do it. One way is what you just said. You have 1 million blocks here. Each block you generate proof, and then you just keep merging them until you only have one proof. Correct, right? That's one way. But that's not efficient. And sometimes, many times you cannot do it because it's not going to be efficient. What I'm saying is, for example, right? For example, you may not be able to hold all of this in the memory in a single computer.
right.
This is one thing, right? This is doable, but I'm saying a more efficient way to do it would be like this. So for example, at Genesis 1, Genesis block, you produce a proof. This one is good. Okay. And then block 1, you produce another proof. This proof says the current block is good, and also the previous proof is also good. So you are not merging this like in a tree. Instead, you are merging like a linearly. So you every time, if you have a pi n, you are saying this pi n minus 1 is good, the proof, and also the current block is good. So this is, so you never end up, the memory usage is like a bigger one. It's not dependent on the how many blocks you have. Does this make sense? So here you still have to put all this proof, merge when you merge, right? You have to put multiple proofs in your memory and generate proof for it. But here you always only have one proof. So you do this iteratively. Whenever you mine a block, you can think of, you create a proof, and then you want the next block, you create another proof. You don't do this just in one single run.
Okay, so if we take W1, is W1 going to validate the proof of W0?
Yes.
Okay, so it's going to validate the proof, but it's not going to have to recalculate the validatable outcome. Right?
Yeah,
okay.
That's the whole.
So each block to the right, it becomes the same, roughly the same computational power to run validation, not to find a solution.
Yes.
So you've built in the finding the solution to each previous proof or block, meaning that it's always going to take around that same amount of time to validate the last block, which is also validating all the blocks before it.
Yes.
Which is that 100 and something milliseconds.
Yes.
1,000 something milliseconds per proof. Okay.
Yeah, exactly. Yes. That's the help. Yeah, now you kind of see the power of this scheme, because it doesn't matter how many blocks or how many steps I'm going through. At the latest, when I'm generating the latest proof, it's always going to be constant complexity. The prover and also the verifier, right? I think Brandon's asking, the new proof is each proof its own unique circuit. New prover key each time. Okay, so let me repeat this question. Brandon is asking, is each proof does each proof have its own unique circuit? And also, if so, does this mean then prover has to do you have to generate the new pair of proving and verification key? So yeah, good question. It all depends, right? It depends what the function you are trying to prove. If there is structurally the same, right? For example, here, I'm just generating the proof after each block, right? Incrementally. because the circuit is same, right? Because you are generating, when you are proving each block, the logic, you can think of each block is not unique, right? So you don't have to, in this case, the function is the same across, when you're doing here, you can see even f, right? This f is constant. It can be roll up, you are verifying transaction, or you can be a blockchain, you are verifying each block. So if the circuit, if the function you're proving, so always can go back to the original, setup, right? So the circuit only depends on two things. One is the function you're proving, and second is, of course, we are assuming the so-called randomness. So let's forget about randomness, because randomness, if the function is the same, we can always reuse the same one. So you don't have to, in this case, if the function is the same, pretty much you don't need to devise a new circuit for each new proof you are generating. So, and all by extension, you don't have to generate new pair of keys. If the function remains, you don't have to do this. So the only other case would be, hey, what if the function changes every single time? I don't have good example for this, but yeah, only if the function also changes, you have to change the circuit, and also by extension, you are changing the pair of keys. So I think a recursive pretty much means the function you are doing is the same. It's just it's like any other recursive scheme, right? The function is the same, but you are just applying on a smaller prompts. Sorry about this. It's okay. They're still joining, but I just keep them out. Okay, now I have to make sure I know people who join in this. Okay. Okay, let's keep going. Make it more legit.
I think we need a web of trust for joining.
Yeah.
Yes.
Right?
Or like, yeah, recursive proof, you have to know somebody who knows somebody. Yes.
Yeah.
That can be another
That's
application.
good.
Yeah, just, okay, you need to establish web of trust. Okay, that's could be another good use case. Real application for maybe that's the whole point. This guy joins. He wants to learn.
I have a
So-
question.
Yeah,
Oh,
sure.
Go ahead.
Okay, real quick. We've been talking at a high level about validation, but it seems like what's missing is some type of inclusion proof. So for example, I may know the proof at the end of the chain, Z of n, but if I have a block header, I don't have any proof that my block header is included in the chain. So it seems like there needs to be a validation proof and some type of inclusion proof.
Yeah, great. I think I think you and Brandon asked almost the same question. I think, yeah, I use this example. Yeah, let me know if by end of this slide you are, if this still does not answer your question. Okay, so basically here, okay, let me come back a little bit here. So let me try to rephrase your question. Basically, you are saying, let's say I'm validating, I'm generating another proof pi1 here, and this pi1, it says, okay, pi0 is good, but also it means, but also in addition to pi0 is good, it also means, generate another, it also shows this thing, hey, the current, let's say block is digit. So here, pi2, not only this pi, let's say pi n, validates the pi n minus 1, but also it also verifies something else. It can be saying, hey, this block is actually chained to this block. Does this make sense? So when you generate a proof n for n minus, it not only shows pi n minus 1 is correct, but also it shows something else. Whatever it is, it can be a blockchain, where you are saying, hey, this block that's contain the the hash that point to the previous block. It has something else. It's not I think that's what you mean by inclusion. This actually is a chain of transaction. We are meaning this big transaction is consecutive. It's not something you just plug in, you just find some anything else, you just put in here. It's not. Does this make sense? Okay, so I think I give more concrete example here. I think also Brandon just asked about is this related to the ancient so-called back to the Genesis solution? It is, yes. So for people who have not heard about the back to Genesis problem, basically, on high level, it's very simple. So let's say I have a transaction 0, which some people call it the Genesis transaction. And let's say, for example, assume all of them only have one input and one output, for simplicity, but you can generalize it. That's for simplicity, each one has only one input and one output. And then you are spending transaction 1 spending from the UTXO from the output of transaction 0, and transaction 2 spending from transaction 1, and you keep going. And then here is the problem. Here's the problem statement. So let's say I just give you transaction N. How do you know it originates? There's an unbroken chain of links tracing all the way to this specific transaction. How are you going to know that? So what's the naive approach here? Anybody? If I just give you a transaction, I ask, hey, does this transaction can be traced back to this specific transaction? How do you do it? How do you answer this question?
Like a brute force link.
Yes,
Right.
exactly. Yes. So what can you think about maybe a more efficient way to do this, especially after what we have been talking about today? Anybody have a guess?
Well, yeah, if there was a circuit at TXN1 that could verify back to TX0, then you wouldn't have to run all the way back to TX0.
Yeah, exactly. Yes.
Yeah, like a token rollup.
Yeah, it's a different kind of rollup, because in rollup, pretty much you are saying, all this can be independent. You see what I mean? So it just says this transaction is legit, this one is legit, but there's no relation between if they are chained or not. This one, for example, it can be Alice paying Bob. This can be, let's say, some crypto files game. This can be, round token transaction. There could be, rollup. Usually they can be anything. But in here, we are just saying, hey, this is a chain of transactions. So I think it's a little bit different. Do you see what I mean? But it can also be, from different transactions, applications as well. So let's get more concrete, more specific in here, right? So we just talk about, how the high level idea using recursive proof. So how what does it mean exactly? So meaning, if you, okay, this one is legit, I'm sure. Okay. Another real person joined. Okay. So we can say, hey, this is we have a chain of transactions. This is a transaction N. So in this step, we want to prove, the validity of a, the following statement. So first part says this proof is good. So what does this prove? This proof means up till this TXN, they all can be traced back to TX0, the Genesis transaction. Right? So that means in proof N, I'm proving two things. One, the previous proof is good, okay? And second, the link does exist, right? So how do I prove the link, right? So if this is one transaction and this is another transaction, how do you prove the link? You pretty much says this transaction ID that's in your input points to the previous transaction, right? That's it. So you're proving two things. One is this previous proof is good, and also the chain that's actually a chain from this current transaction to the previous transaction. Does this make sense? And any question?
Yes.
Okay, so with the previous incremental verifiable computing example, we know, right? Then if I have transaction n, doesn't n can be 1 million, 1 billion, 1 trillion, doesn't matter, right? You give me this proof, I verify it. If this proof checks out, I know it definitely coming from all the way from the Genesis transaction. I don't have to go back 1 trillion times. You just give me this maybe a few kilobytes, I can verify in milliseconds. So how does it integrate if you want to devise a, let's say, tokens protocol, NFT, we have one input, one output. I mint some NFT here and it changes hand for like 1 billion times. How would I make sure, if I don't want to rely on some third party, I can here, this is the only way I'm aware of, you can do that. So, and it's very compatible with the peer-to-peer transaction model of Bitcoin. For Alice, now he has this so-called NFT. He can just give it to Bob. Before he only give a transaction, right? So in addition to this, you can also give this proof. Hey, that's actually coming from the mint transaction. So Bob receive it, he checked the proof, it's good, and then he can do it. He can just accept this transfer is legit. He doesn't have to. It's almost like he's accepting Bitcoin. He doesn't have to go to any, indexer, Oracle, or any server. He can just verify himself. So another way to, I think of.
Wait, hold on. In this example, is Alice sending Bob TXID n-1, and Bob is creating TXID n by broadcasting, or is this as TXID n already occurred and he's using the proof to verify its occurrence?
So in this case, he's pretty much he gives Bob the whole thing, transaction n, not only ID, he gives the whole thing.
Okay.
And also the proof, this proof, right? Pi n. So Bob receives it, he knows, okay, let me hash it. I got this transaction ID. I can use this and this this is the public input. I can check, I can verify this proof is legit. If this is legit, and this transaction also I can verify it, right? Use SPV and whatnot. So it's good. I'm thinking of, okay, this FD is legit, right? Because the transaction is valid, and also it originates from the main transaction. So if I know there's two things. I know this is the real FD, is legitimate. So another way I think about this is, before the whole 0-knowledge proof thing, you can all think about when you give me this transaction, let's say a Bitcoin payment, right? Not only you give me the transaction, but supposedly you also give me the SPV proof, right? So right now is in addition to the SPV proof, you also give me like a token proof. So SPV means, this is a real transaction or the inputs are valid, but here.
Okay, that makes sense.
Yes, so it's a token. It doesn't change any semantic. It's just, instead of sending this Merkle proof, I also give you a few kilobytes of, 0-knowledge proof saying, hey, there's some other property for this transaction. Okay. So
this is only useful for like tokenization for tokens.
I think that's not necessarily, just FT is a good example to demonstrate the usefulness. You can think of, so it's because this is more generic, right? Because you are just improving some generic property. It can be say, hey, this transaction, for example, this transaction, let me come back. This transaction comes from here. You can also have arbitrary other property, right? For example, you can say, hey, I just think out loud. So you can say, this can come from, for example, these two transactions, not only they're chained, but they are in consecutive blocks. I don't know, just think out loud. It can be any computational property you want to prove, right? You can say, hey, this size must be smaller than 1 kilobyte, or this one may contain the signature of Alice. It can be arbitrary. This is just one example, you're proving the chain, the transaction are linked, but it can be any other property you want to prove.
Okay.
Yeah, it can be any, pretty much a mathematical property. You can say, hey, this has to have 3 outputs. This has to be include in block 9, whatever. Yeah, it can be say, hey, this one must have a proof, you're coming from Genesis block even, it can be arbitrary.
Got it.
Yes. So as a, just also like an open issue, I think I post to the community, we just talk about how to use recursive zero knowledge to solve the so-called back to Genesis problem. So, and we also showed how you can, based on that solution, how you can devise a new FT protocol. So of course, you can think of there's some missing pieces. I think that's just a demo I just showed. And in reality, of course, as I just said, right? How do you enforce there's only one output or there's only one input, right? You can enforce it in different ways. So in general, you can enforce it 2 ways. One is you are enforcing this in the zero knowledge itself, because in a zero knowledge, you know the transactions, right? You know the current transaction. You can parse it in the circuit itself, right? You can say, hey, I have only one input, only one output. That's one way to enforce it. So coming back here, so here not only you are saying the pi n verifies this pi n minus 1 is good, and also the chain is good, the link is good. But in addition, because you can prove anything, right? So you can also say, hey, this current transaction can only have one input or 2 inputs or 1 output. You can put an arbitrary constraint over there too. It's just a new circuit, right? Just a bigger circuit. So that's one way you can enforce it. You can enforce it at the zero knowledge, the circuit level. You can also enforce in the smart contract level, right? For people who have, for here, probably you heard about the outpush TX technique, outpush transaction. So you can also enforce it in the smart contract level, saying, hey, I can put that in the Genesis transaction, this smart contract, what does this smart contract say? It says any transaction, following transaction spending from here, you can only have 1 output. So that's another way to enforce it, right? So, and it's very flexible, right? You can enforce it in circuit, what the transaction look like. You can also enforce it in smart contract, but also you can enforce it in both, right? By mixing them together. So you can say, hey, I enforce 1 output for whatever reason in the circuit, but also enforce that only 2 inputs in the smart contract level, because I want to show, that's a fee paying input. Every time I only have 1 output, that's where the FT is, but also make sure, you can have a additional input to cover the transaction fee. I can put this in the smart contract as well. So I pause here. I think this is I've not covered this in my example. This is more like implementation details. So any comments here?
I have a question about the protocol. Since there are many statements that could be made about this, about the back to Genesis hierarchy, so Bob, the verifier, should also know something about the circuit or the proof. Like I'm receiving a proof from someone, but is this proof about the transaction validity, or is it about the number of inputs? So it seems like Bob needs to know, not just run the proof, but know something about the semantics of the proof.
Yes, exactly. So if you remember the 3rd step when you verify, I think I'm not putting everything here. Basically, when the verifier runs, it needs the proof, but also needs something else, right? Namely the verification key, but also the so-called public inputs. So in the verification key, you can think of this is almost encode the circuit, right? For example, you are that's verification key should also be public, right? So it's like proof key and verification key. The verification key pretty much
it could be published. It could be published on a blockchain. Those verification key.
Yeah, that can be that's one way, but it doesn't have to be. It can be, yeah. In Bitcoin is very cheap, so it's a few. There's a few. I think usually it's like a kilobyte or so. So you can definitely put it on blockchain, but it doesn't have to be, right? So you can think of this verification key is almost like a signature or hash of the problem you are trying to prove. In this case, back to Genesis. But yeah, that's good observation. Yeah, I think you have proof, but I think implicitly the verifier also needs the verification key and also some public input. So in public input here is pretty much the transaction ID. So anything you don't want to keep 0 nonce, you don't hide, you don't want to keep it private, that's considered as public input. So here, for example, you public input, hey, this transaction ID is actually, hash of this, double hash of this, right? So you can make sure this, first of all, this transaction is good. And also by looking at the verification key, this is proving the circuit for back to Genesis. It's not proving some Sudoku or anything. Make sense? Okay. And any other question?
I have to jump into another meeting, but I just wanted to thank you again for having these. I'll send you a direct message with some questions, or maybe just prep up for next week, but thank you.
Yeah, anytime. Yeah, you can send it in the Slack, so that's good. All right, thanks. It's almost at the end, so it's good timing. Okay, I think the last one I just want to quickly mention is we just talked about the NFT example, right? So you could imagine it's not beyond imagination. You can somehow extend it to fungible token. It's a little bit more involved, right? Because here, not only you are proving there's a link, right? But also you have to check the balance is good, right? So I just give out some high-level examples for anybody who's watching. You can go ahead and try this out. I think it's doable. So the only challenge here is, fungible token, you only have transfer. And for NFT, non-fungible, you only have transfer function you want to verify, right? So here, instead of only transfer from 1 to 1, you also have two other examples. One is, split, right? So let's say I have 100 tokens here, split into 70 and 30. So this is split. In split, you want to check, this is sum is good, but also, this also originates from the issuance transaction, and you're also proving the sum is good, right? This one plus this one is good. So that's it. A little bit more challenging one would be this, merging. You have, let's say you have 30 and 20, you want to merge to 50. So here you want to check, okay, this is legit, meaning it comes from the Genesis. This one's legit coming from the Genesis, but also the sum is good here too. So the problem is here is a little bit, you have to think carefully, because this is not a single chain. It's kind of like a DAG, directly a cyclic graph. So I think you have to be careful when you're proving the back to Genesis. I think there have to be some case you have to cover, but I think it's doable. It's just the circuit is probably much bigger, and you have to do more checks, but there's nothing stopping you from, you applying the same technique to solve the fungible tokens back to Genesis problem. Any other things regarding this slide? Okay, if not, let's go to the final one. I think it's the final one is just, I want to mention this tool. So previously we've mentioned about two tools, right? One is Socrates and the other is a Circle. So they can use to pretty much producing the zero knowledge proof for arbitrary statement. You can have the high level language, you can generate proof, and you also verify proof. In addition, because we are in blockchain space, the Bitcoin space, so you can also export the verifier in script code. So you can use it to verify it on chain. But here's only one drawback, only one shortcoming for them regarding the topic we're talking about today. Unfortunately, it's not easy to program recursive snarks in Socrates and Circle. So if you want to program recursive snarks, I recommend this tool called Snarky.js. So it's a TypeScript. You can think about a library. So you can just Google this Snarky.js, and there's some good examples. For example, you can use this to prove to show Fibonacci sequence. For example, you can prove, the 1 billionth number is equal to X. So you don't have to go back, 1 billion times to recompute everything. You can generate this proof and give it to me. I verify it. If this checks out, I know the 1 billionth sequence of Fibonacci sequence is, let's say, X. I don't have to go back all the way. So I think for details, just search for this. I think I'll also put in the show notes. If you want to do recursive snarks today, I think this is the only one that's usable I found today, Snarky.js. And that's also what we use to prove the vector genesis, what we use in our internal implementation too. So I think that's we just reached a 1 hour mark. So any concluding remarks or questions, comments? Oh, it's good. Okay, seems all good. So okay, I have one. Okay. All right, so let's call it a day, and hopefully we can see many of you next week. I'll post a video shortly. Thank you, everyone, and enjoy your Friday and a weekend ahead. Okay, bye-bye.
Thank you.
Thank you.
Bye-bye.
Okay, bye-bye.